Cement is one of the most important materials in modern civilization. Hidden inside almost every bridge, skyscraper, highway, tunnel, and dam is a substance that begins its journey deep inside the earth. But how is cement actually made? The process starts in massive limestone quarries. Limestone, rich in calcium carbonate, is extracted from the ground using powerful drilling and blasting equipment. Giant excavators and haul trucks then transport the raw rock to the crushing plant. Here, enormous crushers reduce the limestone into smaller, more manageable pieces. Other raw materials, such as clay, shale, iron ore, and sand, are added to provide the precise chemical composition required for high-quality cement. The crushed materials are carefully measured and blended before entering a grinding mill. Inside the mill, powerful rollers or rotating mechanisms grind the mixture into an extremely fine powder known as raw meal. But the most important stage is still ahead. The raw meal is transported into a preheater tower, where it is exposed to hot gases from the cement kiln. Temperatures rise rapidly, removing moisture and beginning a series of chemical reactions. The material then enters the heart of the plant, the rotary kiln. This enormous steel cylinder rotates continuously while temperatures inside can reach approximately 1,450 degrees Celsius. At these extreme temperatures, the raw meal undergoes a chemical transformation known as calcination and then sintering. The result is a hard, dark gray material called clinker. Once the clinker leaves the kiln, it must be cooled rapidly. Powerful air coolers recover heat from the hot clinker and return much of that energy to the production process, improving efficiency. The cooled clinker is then transported to another grinding stage. Here, it is mixed with a carefully controlled amount of gypsum, which regulates the setting time of the cement. Depending on the type of cement being produced, carefully selected additional materials may be introduced into the mixture. Limestone can be added to modify the cement's properties, while industrial byproducts such as blast furnace slag or fly ash may be used to improve performance and reduce the environmental impact of production. The exact proportions depend on the desired cement grade and its intended application. The blended material then enters powerful cement mills, where massive grinding systems reduce it to an incredibly fine powder.
Grinding circuit 3 is holding steady.
This stage requires enormous amounts
Adjusting
of
feed
energy
rate to
and precise
optimize.
control. The final particle size is critical because it directly influences how quickly the cement reacts with water, how easily it can be mixed, and how strong the resulting concrete will become. What emerges from the mill is the finished cement, a fine, carefully engineered powder that will eventually be transformed into concrete and used to support buildings, highways, bridges, tunnels, dams, and countless other structures around the world. But before the cement leaves the factory, it must pass a series of strict quality control tests. Samples are continuously collected and analyzed in specialized laboratories. Technicians measure its compressive strength, fineness, chemical composition, setting time, and other physical properties. These tests ensure that every batch meets precise industrial and safety standards. At the same time, automated control systems monitor temperatures, pressures, material flows, and grinding conditions throughout the entire production line. Advanced sensors allow engineers to detect even small variations and make adjustments in real time, maintaining consistent quality from one batch to the next. Once approved, the finished cement is transported to enormous storage silos. These towering structures can hold thousands of tons of material, protecting the cement from moisture and contamination until it is ready for shipment. From a limestone quarry to a modern construction project, cement production is a remarkable combination of geology, chemistry, massive machinery, extreme temperatures, automation, and precision engineering. Every bag of cement represents a complex industrial journey. And behind every building, road, bridge, tunnel, and dam lies this extraordinary material, one of the fundamental ingredients of the modern world.